from the shoulder. Get that. Go off. There we go. All right, so we're thinking of the r vector as coming from the shoulder out this way. So if that's r and we cross r with f, we put our hand in the direction of r and we wrap towards f, then our thumb is going into the board. Start with r, go towards f, then the thumb is in the board. That's right. Nice.
That is interesting.
All right, so you go in the direction of the first vector, your fingers curl in the direction of the second vector.
Okay.
So if f was pointing up, we would be coming out of the board. Yeah,
Okay.
exactly.
Okay. Cool.
So r cross f comes out of the board.
What if R was facing the other way?
Well, you go in the direction of r was pointing that way.
Yeah, like if F was on the other end.
So if we moved f over here, oh, all right. Why do I even try to do that? So if f is over there and r is pointing that way,
It's just you just
so
do
if
the
r is
same thing.
pointing that way,
It's still the same. Okay.
yeah, yep.
So wait, you
And
said
if R is
it's,
up on that side.
it's going into the board or coming out of the board? R cross F.
R cross f is going in. Oh, who wrote that? It goes in. The first 5 minutes is always so hard. Gotta get the flywheel spinning. Okay, so yeah, R cross F goes into the board. Into the board. All right, other one from the homework you want to talk about? Question?
How do you know when to go clockwise and counterclockwise? Because if you're going R to F counterclockwise, then it would be coming out of the board.
So whatever vector is first. So if it's R cross F, you start with R, your hand goes in the direction of R, and then your fingers curl
Okay.
towards F.
Got it.
Yeah.
So if we were doing the cross product of F and R, it would go up and
Opposite direction, yeah, exactly. So if we did F cross R, if we start in our hand with F and then go to R, then it's going to come out of the board.
Oh,
Wouldn't it
actually,
be
we go
going
down
down?
and over. So it'd still be going out the board.
Say that again? If we did F cross R,
Yeah.
But your hand should be going the other way because
Yeah,
the
it should be
vector's
going
pointing
down. Right?
but if we do F cross R, we can translate. So we just said we can translate these. So if we put them like that, so we can always translate them, and it will be the same answer. If we put, it's easiest to see if you translate and have the shared point. So if you do F cross R, it's going to come out of the board. If you do R cross F, it's going to go into the board.
But the direction of why are you not orienting your hand in the direction of F? The vector is pointing down and you're putting your hand up. Does it matter?
No, it does. The arrowheads. No, it doesn't matter.
I think they absolutely matter, honestly.
No.
I'm just going to argue with you, man.
Well, yeah, so if we're doing F cross R, the hand is going down and then curling up to R.
Yes, this one's like that. But
Oh
if
yeah,
it's
I guess
pointing
you're
the
right.
other way
I guess it
around-
did. I did it in my head unconsciously. I'm going down with F and then curling towards R. Yeah, you're right. It does matter. Unconsciously. That way.
Oh.
Yeah. But
Now if you do R to F.
so if we do R, if we go in the R direction, we curl towards F, we go into the board. Yeah, yeah, okay. So
F and R.
the orientation of your hand matters. This is not what this class is about. All we care about 99% of the time is the magnitude of the cross product.
Okay.
We don't.
I just want to understand.
Yeah. I just want to understand.
They don't teach you in physics. They just tell
They
you.
don't?
They
That's
just-
the class where you're
they
supposed to
ju-
be able
they
to
just
curl your
tell
hand better
you.
than in here.
They tell you. They show you for like 2 seconds. They're like, yeah, you just do this, and then you're like, what?
Usually in math, we just show you for 2 seconds and say it's going to go perpendicular. That's the most important thing for a calc perspective is that it's perpendicular. That's the most important thing, is that it's perpendicular. So when we're finding the equation of a line, it doesn't matter if the direction vector is this way or that way. It doesn't matter. You can use either one. So for us in calc, it's usually just the magnitude or the loose direction. You know, it doesn't matter if it's off by 180 degrees. You know, and if you're tightening a bolt and you want to loosen it, just go the other way, right? In practice, it's not going to matter too much. Okay.
So, I have a question about this. Like, if this is true,
If this is true.
then why is it that when, like, if I were to hold a dumbbell out at arm's length, why don't I feel my arm getting pulled this way or this way?
Your joint is getting pulled that way. So when you're holding the dumbbell, there's torque on your shoulder.
I can't feel it.
Yeah. Go ask your anatomy and physiology teacher that one. That's a good question. So, but the torque that's happening right there, it's rotational, right? So when you're holding it up, right, you're feeling a spinning motion or spinning sensation right there, right? You're feeling a pivot right there, right?
But not one that's going like out that way.
So,
Right
yeah.
now. Right now.
All right, we are.
Hold it out, and then you'll notice
Oh,
it's gonna try to pull
how
it
did I
up.
get here?
But that might be
All right,
the way
let's go to the
back
next slide.
He's like, moving on.
It's weird.
We're supposed to be thinking abstractly, not so concretely. All right, let's. Oh, look at this. Oh, good. No direction.
Wait,
Wait, did we didn't do
It
these.
doesn't work.
Oh, do we have to go back a previous
Yeah.
slide?
Yeah.
Oh, darn.
Down.
There we go. All right.
We're like, no, wait.
We're like, wait, we don't have.
These ones. Okay, so I'll go ask my PT person about torque on my shoulder. Because what day's today? Because I meet with him Friday. This Friday. I'll ask him.
So next Monday.
I'll ask
you
him.
can come
Yeah.
to us with an answer.
No, we do not have class Monday.
Oh, Wednesday.
Right, we have class next Wednesday, not Monday. And you guys don't have class Tuesday either. Is everybody aware of that?
Yeah.
No class next Monday or Tuesday, the 3rd and the 4th, no class.
Not
Well,
Yeah, it's like teacher's work day on
on Tuesday it is, yes. Yeah, Monday's Labor Day. Okay, so here we've got skew lines. Well, we have two lines that we want to decide whether they're skew or not. And skew lines are lines that are not parallel and don't intersect. So this has to be in 3-dimensional space. In 2-dimensional space, obviously, if they're not parallel, they're going to intersect in 2 space. But in 3 space, you can have two lines that exist in parallel planes that don't intersect and aren't parallel. So those are skew. Can everybody see that those are skew? And can you see that there are parallel planes containing this one and this one? So if you have skew lines, there are 2 parallel planes that contain them. Can you see those parallel planes? If I put that there and that there?
Like
Right.
they're flat.
Flat.
They're
Yep.
horizontal. Okay.
Yep, exactly. The
Okay.
way I have these laid out right now, you have the floor and the ceiling, right? Those are parallel planes that
Okay.
could house
So
us.
this
So
means that they exist, like if that was both x direction, it's just different x planes. different portions
yes,
of the X
yes,
plane.
exactly. Different. So this would be z. If we have them horizontal, this would be z equals a constant. Would be this plane, and z equals another
Okay.
constant. Would be that one.
Okay.
Yeah. So distinct planes. So that's what we mean by skew lines. To figure out if 2 lines are skew or not, we have to just show those 2 facts that they're not parallel and they don't intersect. Let's figure out what's going on with these lines. So one thing that we just barely touched on last time is when you're given the vector form of a line, how do you discern a point on the line? How do you discern a direction vector for the line? So when we look at this first one, we can peel it apart like this. We could rewrite this as 3, 1, 0 plus t times 4, -6, 4. Does everybody see how I unraveled that? So last time we started with this, and then we combined our components and got to a single vector form. So now I just pulled out the constants in this way so that I have multiples of t plus a constant. So this is the constant vector, and then we have a constant vector times t. Everybody see how that happens? So what would be a point on that line for sure? 3, 1, 0 for sure is on that line. That's an ordered triple that's on the line. And if you plugged in any other t value, you would get a different point. If you plugged in t equals 1 or 2 or 3 or -1 or 1/2. So plugging in t equals 0 gives us that 1 point. And then what is the direction of the line?
4, -6, 4.
Yep, so that's the direction. And if you wanted to, you could also say 2, -3, 2. That's the same direction. 2, -3, 2 would point in the same direction.
Because it's scaled.
You could scale it by anything. You could divide it all by 4. You could even do a division by -2 or -4. That would also act as a direction vector for the line. Line goes in both directions forever, so it doesn't matter if you start with a vector pointing this way or pointing that way. You can use either as a direction vector. Okay, so let's go ahead and try to figure this out. What we're going to do first is decide whether they intersect or not. So if they intersect, there would have to be a shared point that they have in common. They have to share a point. So the way we do that is set the x components equal to each other. We set the y components equal to each other. We set the z components equal to each other. And what we have here is a system pretty easy to solve because we have more information than we need. Right? We have 3 equations with 2 unknowns. That's really easy to solve. All you need are 2 equations if you have 2 unknowns. So multiple ways to solve this. You can use the elimination method. You can use the substitution method. Either of those work totally fine. And I am noticing right away that the elimination method might work really easily between these 2 equations. If we subtract those 2 equations,
Won't you end up with no variables?
so what happens when we subtract those 2 equations? Exactly. Tell me what we end up with.
You end up with just
3
equals
4t minus 4t is 0.
3 equals 4.
Okay. So this is important to be able to interpret. Sometimes we might get 3 equals 3. Sometimes we might get 3 equals 4. So what does that tell us? That's called a contradiction. So what do you think that means in terms of them intersecting or not intersecting?
Probably don't intersect.
Yeah, don't intersect, exactly. If we get a contradiction, that means they share no common point. So they don't intersect. So if they did intersect, we would get a relationship between t and s. And if we solve for t and got t to be 5, then we could solve for s and get s to be whatever it's equal to. And then those would correspond to the same ordered triple. One on this line and one on that line, but different numbers for t and s.
What if you get 3 equals 3?
So if you get 3 equals 3, what does that mean? They intersect how many times? Yeah, they coincide. Yeah. So if you get a unique solution, that means that they intersect in one place. If you get an infinite collection of solutions, that means that they're actually the same line. So they intersect everywhere. Okay, so now we have the first condition for skew. We know that they don't intersect. Second condition for skew is that they're not parallel. So let's go ahead and look at the direction vectors for each. The direction vector for the top line, let's call it V1. I've got it right here. So V1 is going to be the direction vector for the first one. That's 4, -6, 4. And the direction vector, or I should say a direction vector, because there's an infinite number of them, -2, 3, -2. -2, 3, bless you. -2, 3, -2.
Yeah, it looks like the direction vector of RT is -2 times the direction vector of RS.
So if we look at this, what we see is that V1 is parallel to V2. Everyone agree? So 2 vectors are parallel if there's a scalar multiple of one that gives the other. So like Will said, if we multiply this one by -2, we're going to get the other one. So these lines don't intersect, but they are parallel. So that means that they're not skew. Everyone agree with that? So they're not skew. So this condition here checked, but this condition here was false because skew lines aren't parallel. Yeah?
What if it wasn't so simple to figure that out?
It's always going to be that simple.
It's always gonna, well,
It's always going to be that simple because let's suppose you had these 2 vectors here. Let's suppose you had the vector 1, 2, 3, and then here you had the vector 2, 3, 4. Here you know that these are not parallel right away because this multiplier is 2, but this multiplier is not 2. So you're done right away.
Okay.
So testing whether two vectors are scalar multiples is quite easy because you look at the relationship between the x's, and for them to be parallel, that relationship has to be the same as the relationship between the y's and the same as the relationship between the z's. So it's always going to be that quick to test that part. The harder part often is the system part because you've got to figure out a common solution.
So you don't have to do like the cross product. Let's say if the cross product equals 0, then you figure out that they're parallel.
That's a great point. So if the cross product was 0, that's another way to confirm that they're parallel, correct? Because if you have two vectors that are parallel, and you take the cross product, you're going to get 0 because there's no parallelogram that's formed. So you have no area. So that's another way to test. So when we're talking about parallel and you've got the numerical values right there, it's easy enough just to see if there's a scalar multiple. But that would also be a test. Take the cross product and show that it's 0. Whenever you have vectors that are parallel, that cross product is going to be 0. So yeah, that's another absolutely a good way to go. Let's take a look at this one. So here we're going to set. And the reason that I put all three of these, I mentioned that it's a little bit redundant. We have 3 equations with 2 unknowns, which is pretty easy to solve. So you may say, well, why put all 3 up there? And the answer, if you only need 2 of them, and the answer is we still need to check. We still need to check that all 3 are true. We have to make sure that we get the same exact ordered triple for both lines. Maybe they share 2 coordinates that are the same, but not the third or something. We just want to check make sure that all coordinates match. I have a bad feeling about this one too, I think. Yeah. I just looked and I see a multiple here. If we look at these two right here, and if we do this first equation, if we multiply it by 2, if we do 2 times the first equation and add it to the second equation, 2 times the first is going to give us 8. That's going to cancel. 2 times that's going to be 2 plus 8. 2 plus 6, which is 8. And then that cancels. So here we get
Complete.
an infinite collection of solutions, which means the lines must be the same line. Yeah?
Aren't we subtracting?
Yep, I subtracted, I think. So if I...
4.
So if I multiply that by... No, I'm adding because I'm eliminating the variables. So
Okay,
I'm adding.
Okay.
So if I multiply by 2, 8 plus 0 is the 8, and then 2t minus 2t, multiply that by 2, add that, multiply that by 2, add. So
Okay.
both the s's and the t's cancel. Yeah?
Yeah, I noticed right away that actually, if you deconstructed the things to get the direction vectors, they are actually parallel right
Yeah,
away.
and so for the lines to be the same line, we have 2 things that would also have to be true. We would have to certainly have parallel direction vectors, but we would also have to have an infinite number of shared points.
So the
So-
points at the beginning would be the same?
No, the initial point doesn't have to be the same.
Oh, because they can still be on the same line.
They can still be on the same line with different initial points. But just showing that the direction vectors are parallel wouldn't be enough to say that the lines are parallel, right? Everybody agree with
Although
that?
it would also... Although
Because if they're parallel, they could be the same line or they could be parallel lines. So we have that one extra thing that we definitely want to check.
Would you still get the same result if you chose the bottom 2?
Yes.
Okay. So
Yes. Yeah,
or
so
the
either
first-
way, we're going to get an infinite number of solutions. It won't matter which pair we use to find the s and the t, just like it's not going to matter what the multiple is if the direction vectors are parallel. So if we look at our first direction vector up here, that one's going to be 1, -2, 3. And the second one is going to be -7, 14, -21. So we see that, oh yeah, if we multiply the top one by -7, that will give us the second one. And so this tells us that the direction vectors are in fact parallel. So our conclusion here is the lines coincide. Is that how you spell that? That doesn't look right. Is that right? I can't tell. It's too close to the board.
So
Eric?
what determines whether you add or subtract the two?
It depends on the signs. So when we look here, I see that these two have opposite signs, and my goal with the elimination method is to try to eliminate a letter. So if I want to eliminate the t, and this is a plus and that's a minus, I'm just going to add them. And if I have 2t minus t, then it's going to go away.
So the process is mostly determining just what best eliminates it as opposed to a process of always subtracting or.
That's right. So if we had the left side looking like this, if we had the left side that looked like these, we would subtract then, because our goal is to eliminate a variable. So I want to make sure that the signs are opposite and add, or the same and subtract, just to force it to disappear. So here I would subtract them and end up with 1 and then 0t.
And if the top one was negative 3t, then you would add it to eliminate.
Exactly, exactly. So if the top one was negative there, then we'd end up adding and we get a 3 as that constant on front. That's right. Okay, so these lines coincide. So neither of these two examples gave us skew lines, but this gives us enough information. So if these weren't parallel, you would conclude that they were, in fact. Oh, actually, no, not in this one. In the one above. In the one above. This one fails both conditions. This one up here, they don't intersect, but if we showed that those were parallel, then we would. Not parallel. Oh, those were parallel. So if we showed that they weren't parallel, then we would have skew. So no intersection, not parallel, then we would call them skew. So these ones are not skew.
Is there a way that you wouldn't get two numbers equaling each other when you set the system?
Say that again.
Like both of the examples you got, like a number equals a number when you did that?
So if there was truly an intersection, you would not get a number equals a number. Like the last, I think the last one we, no, it wasn't the last. We did done one, last class. I don't know where it was. There's one that we did last class where we ended up with a t value and an s value, and that generated an ordered triple. What number was that one?
48.
Number 40, number 48. Yeah.
Okay.
Yeah. So that's the third option.
Okay.
Is that you end up with t equals 3s. Plug it in and you get t equals a number, and then back substitute and get s equals a number.
But you can still get no intersection with that, right?
No, that's an intersection.
Oh, okay.
Yeah, if you get t and s, theoretically, let me think about that. If you need to check that the ordered triples match. So if you did two equations and you got t is 1 and s is 2, you would need to just double check that the third equation gives you that gives you an identity if you plug in the 1 and the 2. So you just have to check that all three match. Yeah.
Is it smart to stop at, like, if you get 8 equals 8 and you know, like, oh, those are the same lines, is there any way that they're not parallel to each other? If you get 8 equals 8, do you need to continue to?
Not really.
Okay.
Not really, because
Okay.
if you're showing that there's an infinite number of intersections, then you know that the direction. That's more of a confirmation that the direction vectors were parallel.
Okay.
If the lines coincide and the direction vectors aren't parallel,
We might not be on Earth.
yeah, we're not on Earth anymore. Exactly, we're in a different universe. Different universe, but that is, yeah, you're right. Okay, so line plane intersection here. We have the equation of a plane. So that equation there, z equals -8, is a plane. If you imagine the xy plane, z equals -8 is parallel to it, just down below. And then we have the equation of a line right there. We want to figure out where they intersect. So this is exactly what you've done in algebra. If you have two objects and you want to know where they meet, you plug one into the other and see if there's a common solution. And so in some ways, it's easier in this context than in some of those college algebra problems where you had planes and you were trying to figure out if they intersect. Here, the z value on this, for every single ordered triple on this plane, the z value is -8. So we just want to know, hey, is there anywhere on this line where the z value is -8? So what we're going to do is set this z value here equal to that z value there, and see if there's a solution. And of course it is. We get t is equal to 6. And so now we know that when t is 6, the line has a z value of -8. Well, that means it's going right through the plane at that t value. So at t equals 6, the z value is -8, which means it's going through the plane. So now let's figure out what the but could be going through the plane in lots of different locations with respect to x and y. So now we need to figure out what x and y are. So we go back up and we plug in. So that tells us, oh, we definitely go through the plane. Now we just have to narrow it down. What is the exact point that we're passing through the plane at? So we take our 6, plug it in there, 18 minus 2. Take our 6, plug it in there. So this would be the ordered triple that the two geometric objects share. That's a point that's both on the line and it's on the plane. So that's where the plane is intersected by the line. So same idea, though, that we've used in algebra. Plug one into the other to see if there's something in common. Plug one into the other. All right. Make sense to everybody? So now we have a curve. So let's analyze this. We haven't talked a lot about curves that weren't lines in three-dimensional space. So first off, this right here is a curve in 3 space. One nice thing about vector functions is that you know what the ambient space is. In other words, you know what the dimension of the space that the curve or surface resides in. Because it tells us there's 3 components. That tells us we're in 3-dimensional space. Totally different from Cartesian. If I say to graph x equals 2, there's nothing in that equation that reveals what the ambient space should be. You don't know. You have to ask the next question. Are we in R1? Are we in R2? Are we in R3? Are we somewhere else? So with Cartesian equations, you don't know. This could very well be the graph of that, or the graph of that could be the line, or the graph of that could be a plane. So you just don't know unless you're told what the ambient space is. Nice thing about vector functions, you know. This is 3 components. So if it's 3 components, you know that the ambient space is R3. If there's 1 parameter in here, you know it's a curve. For it to be a surface, there would have to be 2 parameters, like an S and a T, or a U and a V, which we'll tend to use a lot. So the number of components tells us the ambient space. It tells us the dimension of the ambient space. If there was only 2 components here, we're in 2-dimensional space. We're in a plane. There's 3 components here, so in 3-dimensional space, there's only 1 parameter. Doesn't matter how complex those functions are. Those have nothing to do with determining whether it's a curve or not. If this is cosine, sine, tangent, square root of t divided by t to the 50th, doesn't matter. If it's a t, if there's only 1 letter, if it's a function of 1 variable, then it's a curve. Maybe the curve is just a circle, or maybe it's a line segment somehow. All of those mean curve. It's one-dimensional in nature. So we've got a curve, we've got a plane. The idea that we just used above, same thing. We're dealing with a plane. We want to know, hey, does this curve ever pass through that plane? Well, this curve will pass through this plane if, at some point, it has a y component there of 1. So we just have to test. Is the y component ever 1? If it's not 1, then they don't intersect. So does the y component here ever equal 1? So let's see. So we get sine of t is equal to 1/2. And we are told that we're only going to look between the interval 0 and 2 pi. So this curve, it has a start point and an end point. So this tells us that we're looking at the unit circle, 1 revolution of the unit circle. So this tells us that we're going to get t equals what 2 places? 5/6 and
11 5/6.
5/6. So sine is the second coordinate. Second coordinate's positive 1/2. So if we look at a unit circle, in particular, if we look at a 12-sector unit circle, which is a clock, the sine is positive 1/2 at those 2 locations. So 5/6 and 5/6. So where the second coordinate's positive. So it says find the points if they exist. So we're not quite done yet. So our 2 ordered pairs. One of them will be found by plugging pi/6 in up here. So we have 10 times cosine of pi/6. cosine of pi over 6 is root 3 over 2, so we get 5 root 3, comma. We already figured this part out, so this is going to be, when we plug it in there, we get 1. And then the third component's always 1 in this case. So that's one point that they share. The curve passes through the plane at that t value, and it's also going to pass through at this one, 5 pi over 6. Cosine of 5 pi over 6 is minus root 3 over 2. So we get that. And 1 and 1. So those two places would be where this curve passes through the plane, y equals 1.
Why are those not in like a vector thing?
So we're finding points. So we're finding ordered triples. So the idea with a vector valued function is that the vector is pointing to an ordered triple. So it's the tip of the vector that's the ordered triple that is the point that we're looking for. So with the graph of a vector valued function is just the collection of all the tips of the vectors. Okay, so if we're looking for an intersection point, we sort of evaluate the vector to figure out where its endpoint is. So every value of t for a vector valued function generates an ordered triple, which is the endpoint of the vector, and that's the part of the graph. The graph of a vector valued function is the collection of endpoints. Oh, that was it. All right, any other questions on that?
I have a quick question.
Yeah.
Are we ever gonna deal with like the helix?
Yeah, we will do lots of helices. Lots of helices.
Is there one on here?
Well, there is an elliptic helix. Well, no, that's actually just an ellipse. Well, let's talk about this one though, actually. So this is a great question because it's really important to start thinking about what these curves look like, and quite frequently you're going to have no clue what a curve looks like in three-dimensional space. The only time you're going to have a clue is if there's some nice relationship between the variables, which in this case there is. So first off, the z coordinate for any point on this curve is going to be 1. So that tells us that this curve is going to live in a plane z equals 1, whatever that curve may be. It's going to be elevated above the xy plane at z equals 1. Everybody see that? That's how you would interpret that. That every ordered triple on this curve has a z value of 1, which means that that curve's in a plane. So now when we look at the relationship between x and y, if there's a discernible relationship, we might be able to figure out what that curve looks like in the plane z equals 1. So let's go ahead and write this down. So I'm going to just call x 10 cosine of t, y 2 sine of t. And when we have our vector valued function and we pull out those components and set them equal like this, these are typically called the parametric equations for the curve or the surface once we get to surfaces. So when you identify, and let me put the other component on there just because there's no reason to leave it off, even though it's constant. We should stick it on there anyway. So these are the parametric equations for R, for the curve R. So you can sort of write your components out like this in parametric form, or you can write it out as a vector. It doesn't matter. Those are the same thing. And if we focus on x and y right here, if we want to figure out what curve it is, we need to eliminate the t. Parametric curves aren't something that we've grown up thinking about, so they're unfamiliar. But we're very familiar with Cartesian equations. We know x squared plus y squared equals 4 is a circle. We know y equals x squared is a parabola. We're very good at Cartesian equations. So what we want to do is try to eliminate the parameter and turn it into an xy equation. And if we look at these up here, we can say, oh, well, x over 10 is going to be cosine of t. Y over 2 is going to be sine of t. And when you see sine and cosine, there should be an identity that is just screaming at you. And that identity is
Sine squared equals 1.
sine squared plus cosine squared. Yep, is equal to 1. So the primary Pythagorean theorem. Yep, that's the one. Well, let's just do a substitution. That's an identity. That's true for every value of t you can imagine plugging in there. So sine of t is y over 2, so this becomes y squared over 4. Cosine is x over 10, so this becomes, I know I squared wrong. Don't scream yet. All right, so we're going to end up with this Cartesian equation. Everyone agree? So sine squared, we square both sides, so we get y squared over 4. Cosine squared, we square both sides, so we get x squared over 100. And what's that equation? That is
Equation of
an
an ellipse.
ellipse, a squash circle. So that's an ellipse, and if we wanted to sketch that ellipse, we know that the center of it is at the origin, because it's not a y minus or an x minus. So we know that it's at the origin. How many units from the center do we go horizontally? 10. We look under the x's. We take the square root. That means we're going to go 10 units from there to get out to the edge. I'll put it like that and then move it. And how many units are we going to go vertical? Dose. 2 units. So that is 10. That is 2. Yeah. And then to visualize the curve in 3-dimensional space, we're just going to tilt that ellipse on its side. We're going to lift it up 1 unit. So if we were going to try to draw it in 3-dimensional space, we'd be thinking about that ellipse as elevated. It's long in the x direction. So x, y, if we put x here and y here and z here. Very kind of tricky to draw, but we're going to sort of think of it kind of like that. Floating in the plane, z equals 1. Not easy to draw, but kind of get the idea. So now, Diana's question, what about a helix? So a helix, if you were to look down from the z direction, if it was in the xy plane, it would look like a circle or an ellipse. If you were to look down at a spring, some sort of helix. So the difference between this curve and a helix is that this has a constant z coordinate. It doesn't have a variable z. So to make this into an elliptic helix, all we need to do is change that z. If we make that z value a t, then we're dealing with an elliptic helix, because then the z value is changing as t changes. So that's all it would take to turn it from an ellipse into an elliptic helix, is have a variable z value. That's all it would take. All right, any other questions on that? Yeah?
Can we do 11.5 number 1? It's like a parallel line.
Parallelepiped?
Yeah.
11.5.1. Parallelepiped. So parallelepiped is just a what do we call those things? A rectangular prism that's shifted over. So 11.5.
It's like a cartoon or something.
So that one right there?
Yeah.
Do you know how it's fun to go? Slinky, go. It's true. That detective in the very beginning when he's like, the Buddhist temple. I remember that, like, here.
Oops.
Okay.
I think we're in the right place. That's where we just were. So find the equation of the line. Wait, I don't see a parallelepiped. Everyone know a parallelepiped? Like if you take a stack of cards and then just slide it so that it's sloped, that would be a parallelepiped. It's just a tilted box. Parallelepiped. And that doesn't change volume. Cavalieri's principle for volume. Does everyone know Cavalieri's principle? So if you took a deck of cards, it has whatever the volume is. But then if you slid it so that it had a nice like a line, not a curved side, but well, it doesn't actually matter. It could be curved too. But that's not going to change the volume of it, right? So Cavalieri's principle says if you have two objects that have the same height and every cross-sectional area matches, cross-sectional areas at the same height match, then the volumes are the same.
Is that like the napkin?
The napkin ring problem.
Yeah.
Yes. Which I just posted on our front page. I think, no, I did that in Calc 2 because we're dealing with napkin rings in Calc 2 right now.
We don't get videos.
Everyone know the napkin ring problem?
No.
Go look it up.
Vaguely familiar.
Go watch Vsauce do his napkin ring problem. So napkin ring problem, if you take two spheres of different sizes and you core them out so that you end up with rings of the same height. So if you have a ball this big, and let's suppose we want the height of the ring to be that, you'd have to core out a lot. And then you have a smaller ball and you core it out so it's got a napkin ring of the exact same height. So you've got that ring of the same height. The volumes match. So if you take a tiny tomato and you take a huge ball, like a hot air balloon ball, and you core them so that they have the same height, the volumes of what's left will be the same.
Do you mean like height, like the thickness of the ring, or do you mean like radius?
So I mean,
Yeah, it's like instant.
so that.
Hey, Vsauce, Michael here. If you core a sphere, that is, remove a cylinder from it, you'll be left with a shape called a napkin ring because, well, it looks like a napkin ring. It's a bizarre shape because if two napkin rings have the same height, well, they'll have the same volume regardless of the size of the spheres they came from. This means that if you cut equally tall napkin rings from an orange and from the Earth, well, one could be held in your hand, the other would have the circumference of our entire planet, but both would have the same volume.
Yeah, watch that one. That one's a good one.
It's a shame that we don't have the biggest fan of Vsauce in this class.
Who's the biggest fan?
The guy that was in Calculus 2 semesters ago, he just talked about Vsauce like every single day.
That was the first time I talked. I don't remember who that was. But I remember hearing
It'll
it.
come back to me. Yeah, I know who you're talking about now. Yeah. Okay, so this one has nothing to do with parallelepipeds or napkin rings or donuts.
Then who mentioned the parallelepiped?
Rachel! Yo, you did. Did I mention it?
Yeah, you mentioned it.
I thought you said something about a parallelepiped.
She said a line.
Yeah.
Did you say a line?
Yeah.
Am I hearing things? Oh no.
Maybe I'll like email you about it.
It's come, somebody, I thought I heard the word parallelepiped. All right, find the equation of the line through, that's my favorite word to say in Spanish though. Parallelepiped, paralelepípedo. It's like the one Spanish word I know, other than baño and cerveza. Okay, so find the equation of the line through 0, 0, 0 that's parallel to this line where t equals 0 corresponds to the given point. Okay, so if we want a line parallel to this line, that means the direction vectors have to be parallel. So the direction vector for this line will pull out the v. The coefficients of t will be the direction for this line. And that means that has to be the direction for the line we're trying to find. And we'll put that right in here. 3, 5, -3. And then what would be a point that's on the line we're trying to find? Yeah, 0, 0, 0, right there. Boom. So the equation for us for this line would be nothing more than that. So that would be the equation of the line through the origin parallel to R.
Would it be that simple on a test?
If it's not, you should think twice.
Okay.
Calc 3 is weird because you can overthink problems so easily.
It's Calc 2's fault.
Yeah, it's Calc 2's fault because you have to overthink problems in Calc 2. Yeah, Calc 3, if you see the geometry and the relationships, things can actually just fall out really quite nicely. Okay, so that makes sense to everybody? I just have to go to the next slide. Okay, we're done with that unless someone else has a question. Is it time? Not yet. Okay, this, do you guys want to do a problem like that? Let me give you one to do before we start 11.6. Let's not go that far back. So here is one for you to try. So find the line that, I'm going to make it a little harder. So the last one is too easy. So find the line that contains the point, bless you, -1, 2, 4, and is parallel, I can't spell very well. That still doesn't look right. Parallel to the line of intersection to the planes 2x minus, oh no, you don't know that yet. Shoot. Parallel to the line, I'm just going to do that. You need one more piece of information for you to make it more complicated. Darn. Darn. One more piece of information, then we can make it harder. So find the line that contains that point and is parallel to that line. Yeah, we haven't done one other thing yet, which we will do next week. So when you're finding a line in 3 space, you should be thinking just like, yep, and then combine them into one vector.
Oh, you want them together?
Yep, mash them together into one. So yeah, these ones aren't too crazy hard. I guess I could have said parallel to
The intersection of the plane of the line of
I was going to use planes, but we could talk about the perpendicular to both lines, to two lines. That's possible.
Yeah.
But the only issue there is trying to get two lines that intersect. Question?
I thought you were gonna give him a marker.
He looks like he's wanting. Looks like he's ready for it.
You wanna teach?
No.
So for the math part of it, do we just want to consider the t part and the constant part?
Exactly. So when we're looking for the direction vector for this line, we really only care about the coefficient of t. So just like in algebra, when you're trying to find the equation of a line, you have to have two things. You need to have a point. Usually in algebra you say y-intercept and slope. So for us, y-intercept corresponds to a point on the line, and instead of slope we need a direction for the line. So still, same idea though, we need two things. So we're told a point on the line, so we're going to write the point in terms of a vector. So that point being on the line means that the vector I just drew down there will point to that point. The terminal point of that vector will be -1, 2, 4. And then we take the coefficients of t here, so -1, 1, 3. And this book always puts the t in there. I don't have space, I'll just put it over here. Doesn't matter, commutative law. So that will be our line containing the given point and parallel to the given line. So we have -1 minus t, and then 2 plus t, and then 4 plus 3t. So that is our line.
It looks like your original line and your resultant line are using the same name.
Same.
They're both called RT.
Yeah, we do that all the time, right? Y equals 5x, y equals 2x. Right? We do it all the time. If it gives you any sort of heartburn, go ahead.
It gives you hurt.
Okay, that's better.
Is that better?
Yeah, less confusing.
Yeah.
Which do you prefer us, like which form do you prefer us having? Does it matter? Does it not matter?
This form versus
that form?
This is better. When you're asked for the vector form of some curve, you always want it as one vector.
Okay.
Yeah. This is considered the sum of two vectors as opposed to a vector. So the vector form combined everything. Yeah. All right, why don't we take our 10-minute break and then we'll jump into 11.6. 11.6?
What is it in Spanish?
Seis?
The
Parallelepípedo.
Parallelepípedo.
Somebody told me that one time. I was like, oh, that's so cool. That is a very cool. All right, resume. Okay, so this one says, this is the end of 11.5. Before we start 11.6, I put a couple of extras up here for us to practice on. So this says to find the distance between a point and a line using the cross product. So we did the distance between a point and a line using the length of p perpendicular. That's how we had done it in the past. So we're going to do it a little differently here. Do it in a very clever way. So we have a line, and we're going to have a point that's not on the line. So we've been, what are we calling that? Where P is on the line. Yeah, so here Q is not on the line. So that's our situation. We want that shortest distance. We want that dotted line distance right there, perpendicular distance. And one thing that we can always do if we have the equation of a line, we can always find a point that's on the line. You plug in any t value and you can get a point on the line. Plug in t equals 0 or 1 or 2, doesn't matter. So we can find this point on the line very easily by plugging in a t value. So if you plug a t value into the line, that's going to give you a point on the line. And like we just saw a few minutes ago, if we look at the coefficients of t, that will give us a direction vector for the line. And that's what I'll call v. So v is a direction for the line. So just like the last one, if we just look at the coefficients of t, that vector will be a direction for the line. Then we can also form this vector, which we've done. This vector right here, bless you, PQ, that vector, which I think back then the text was calling that vector W or something. I think that's what they referred to it as, W. You can just call it vector PQ also. All right, so we want that distance. Now what we did in the last section, or a couple sections ago, we figured out what P was down here, the projection of W onto V or U onto V, whatever you want to call it. Actually, I guess we were calling it U, I think. We were calling it U, so let's make it U. So projection of U onto V, and then we did U minus P to get P perp, and then we took the magnitude of that. So that wasn't too much work, but there's a faster way. And here's the faster way. We now know the geometry of the cross product. The geometry of the cross product says, hey, if you have two vectors that share an initial point and you cross them, the magnitude of the cross product is the area of the parallelogram. So the area of this parallelogram right here, that is going to be the magnitude of U cross V. Now, what's that?
I hit Diana with my lid on accident. Broken snap.
And isn't the magnitude of V the length of the base of the parallelogram? The magnitude of V? So V is defining that base. If we take the magnitude of V, we get the length of the base. And we have a formula for the area of the parallelogram. Let's call this the height. We know that the area of a parallelogram is base times height. So the area of a parallelogram is base times height. That tells us that the height is the area divided by the base. So that tells us that the height of the parallelogram is equal to U cross V's length divided by the length of V. And that's what that equation is up there. So that is a pretty slick way to get the distance between a line and a point. Form two vectors, one that points to the point, one that points to the point that's not on the line, and one that points in the direction of the line. Cross the two, find the magnitude, divide by the length of the base, and you'll get the height. Height is area divided by base. Let's try it. Height is area divided by base. All right. So I find it useful to draw a sketch every time just to keep things clear in your head, what's what. So this is the picture that I tend to draw in my head, or picture I want to have in my head. So Q is not on the line, so we're doing that. That's Q. What would P be?
1, 3, 1.
So P is going to be 1, 3, 1. We got that by looking at the equation for the line and plugging in T equals 0. If you plug in T equals 0, 1, 3, 1, that's probably the easiest point to use. You could use any point, though. You could plug in T equals 1 or any other constant. And what is going to be the most obvious choice for the direction of the line?
3, -4, 1.
3, -4, 1. Perfect. 3, -4, 1. So that's the line's direction. Now we can form a cross product between two vectors. We can form the vector u over here, and that vector u is going to be found by doing, let's see, it's going to be doing the terminal point minus the initial point. So 4, 3, 0. Now I'm going to put vector v right under it. So then we can do the cross product. And it doesn't matter which order, if we do u cross v or v cross u, because we're only interested in the magnitude of this vector, not whether it's pointing up or down. Doesn't matter. So cross product. Let's see if I can do that right. Cross out the first column. And then we do main diagonal product. 3 times 1, so we have 3 minus 0. So that's our first component. Second component, cross out the middle column. We can do main product minus other product, and then change the sign. Or you could just simply do other product minus main product and get -4. And then third component, cross out the third column, -16 to -9, -25. So that is our cross product. So the area of the parallelogram, we take the length of that, take the magnitude of that vector. Magnitude of that vector will give us the area of the parallelogram. So that's going to be 9 plus 16 plus 625. So the area will be the square root of 650.
Which is 5 square root 26.
Thank you. Now we find the length of the base. The length of the base will be the magnitude of vector v. So we find the magnitude of vector v. That will be the square root of 9 plus 16 plus 1. Square root of 27. Now we have the area of the parallelogram. We have the length of the base. Take the area, divide by the base, get the height. Got it.
Square root of 26.
Say that again?
Square root of 26, not square root of 27.
10 plus 16 is 26. Okay. I buy it. Thank you. Oh, that's going to simplify nicely. Yeah. Yes. Excellent. All right, so we do area divided by base. So that's going to be 5 square root of 26 divided by the square root of 26, and that gives us 5. So that's our height. That's all right. So if you want to do it the other way with P perp and P, you could do it and see that you get the same thing. You will get the same thing. Lots of geometry.
When you do U cross V in the second component, is it supposed to be a positive force?
Let's double check. So when we get the middle component here, we're crossing out the middle column, and then we do the main product minus the other product, but then we switch the sign.
Oh, okay.
Or cross out the middle column and you can do other product minus the main product and leave it. So yeah, so it will be negative in this case. Will be negative. All right, you ready to try one of those ones? Try it out. So you find the distance between Q and line R. Find the distance. Yeah, let me know if you need any nudging, any lubrication. So that, get that coefficient of friction down close to 0. That eraser is not one piece anymore. Sure how that connects to it.
Looks like part of a chair.
Oh, that's part of the chair. Seems awfully large eraser. Sketch the picture as you blaze through the front. 0. Mad math.
Breaking my butt.
What is this?
So that's the cross
Stop
product.
products or cross products?
Cross products. Yes, cross products. So the cross product of two vectors is another vector. Whereas double.
So for this one, I want to consider 0.
I feel like these are really big numbers.
And minus
169.
the first one is the left hand.
Yeah, yeah.
So, and then
25 minus plus 1.
This would be the negative of.
Minus 1. It's 25. Minus
12. Yep. Yep.
Maybe.
119 and middle one I changed the sign so that means
Yeah, and so it depends on which direction you subtract. So if you do Q minus P, negative 5
Okay,
minus
so
negative
that's
5.
like a really big
Not that that's so much. That might affect. That could affect it. All right, let's go through this one.
It's a really big number.
So negative 529. What's a point on our line?
724.
That's one, definitely. We could, if we wanted to, we could pick a different one by plugging in t equals, say, -1. That might, okay. There's a couple of ways to make that point maybe have less magnitude in it. Doesn't matter, though. The natural choice is to plug in t equals 0. So 7, 2, 4, is that what we said? 7, 2, 4. Okay, so if we do that, then we're going to form our vector u. Vector u is going to be qp, or actually I should call it pq, from p to q. And so that would mean that we do q minus p, so what's that, -1205? So that'll be our vector u. And then our vector v is pretty easy to find because vector v is found by looking at the coefficients of t. So 5, -112. 5, -112. Everyone okay with that? So then we just cross them to find the cross product vector. So u cross v. First component, we cross out the first column. Main product is 0 minus the other product, so that's -5, which is 5. Middle column, our main diagonal product is -144 minus 25, which is -169. We switch the signs, we get 169. Third, cross that out, we get +12 minus 0. Oh yeah, that's a pretty hardy area here. So the length of this will be equal to the square root of, what is that number when you add all that up?
13 square root of.
Say it once again.
13 square root of 27. 127.
13 square root of
127.
127?
I got 170.
Oh, 170, yeah.
Oh, 117.
70.
170.
170. All right. Cool. Thank you.
That should be -169.
I think.
That should be -169?
Or no?
So it's -144 minus 25, which is negative, but then we switch the sign.
Okay.
All right, so that is the area of the parallelogram. Now let's find the length of the base. The length of the base is the magnitude of v, which is 25 plus 1 plus 144. So that's going to be the square root of 170. Oh, how convenient. Huh. So then the height is 13 root 170 divided by root 170. So the height is 13.
What if we want it to be 170 times the square root of 13?
What's that?
What if we want it to be 170 times the square root of 13?
If you want it to be that?
Yeah.
You could write that if you want.
Is there a reason to do it when
I've got a nice bright red pen. So when you multiply, when you square, add, it just turns into, if you were to look on the inside, I guess apparently 13 squared times 170 is going to be whatever that's equal to. So you're just pulling out perfect squares. Now if you didn't pull out your perfect squares and you got down to here, if you just left it as the square root of a big number, that 170 would divide in and end up giving you 169 inside, and the square root of 169 will give you the 13.
Okay.
So you could just wait to
But
the
it'd be
very
more
end.
pain.
You could wait to the end, yeah.
If I switch the number, the P and Q,
Uh-huh.
I got the same answer, is right?
Yep. Because it doesn't matter whether you subtract this way or that way. Once you find the cross product, it's the same parallelogram. Yeah, when you find the area. Yeah, it won't matter. Good point. All right. Let's leave this one for now. We've done enough of these, I think. You want to do one more? Or? You do? All right, go for it. Let's see how fast you can do it. Ready? Go! Let's see who gets the answer fastest.
Oh boy. No.
It's a race.
It's a race! Go!
It's on, Hub. It's on.
After so much, it's just the obsessive.
you racing too?
Fine.
Ugh.
Go.
I need the exam. No big deal.
Oh, this is good one.
I feel like you have an unfair advantage.
I know. Okay, I'll go slow.
It would seem that way.
It's not like you know exactly what you're doing or anything.
I don't have a calculator.
Oh, that's his disadvantage.
It was like pretty color.
Yeah.
I might need to borrow one for this.
Your pants to become full force Shouldn't your QP be 6.6 -3?
Hey, you're helping out.
You could either, whatever direction, you're going to use 0, 0, 4, so it's 6 minus 0, 6 minus 0, 7 minus 4, or 0 minus 6, 0 minus 6, 4 minus 7.
But because you wrote it as QP and not PQ, doesn't it have to be?
So then I should be doing, I should be doing P minus Q, you're right, yeah. So I should write this as PQ then. Good point. Yeah.
H equals 9.
What's that?
H equals 9.
H equals 9.
I disagree.
I disagree with
I got
that.
173, square root of 173.
You got square root of 173?
Yes, sir.
I got 9. I got 9.
9?
I'm still working.
Hurry!
Same.
Hurry! We need to know if it's 9 or square root of 173. Keep going!
Well, you got 9.
Well, I just wrote what he said. I didn't have a calculator to figure this mess out.
Yeah, I think Shel Silverstein did something like that.
31 plus 36.
A bunch of people copied one person, but the first person got it wrong.
Yeah, then it's a mess.
No one got caught, but Susie was wrong.
Oh, I agree, 9.
Yes!
9.
First.
9. All right. You win the opportunity to bring us snacks.
On Monday.
Yeah, I'm not Monday. I'm Wednesday. All right, so any questions on any of the steps? I think this over here. Let's see. So the vector, do you agree with these?
Yeah.
You have those exact lines? Okay, so then with the middle one, we're going to cross out that. We're going to do 9 minus 0 and change the sign.
Okay.
So then that would give us a negative. If you went that way. Okay. Let's talk about 11.6. Finally. Finally to 11.6. Finally to 11.6. The idea now is that we want to do all that calculus stuff that we did before in Calc 1 and in Calc 2, derivatives, integrals, but for vector valued functions. And last time I mentioned that it's not too hard because if we have a vector with 3 components, we take the derivative 3 times, we take the integral 3 times. It's not that complicated. We just have to do things in triple. So first off, when we do a derivative, we do it term by term. Typically, I'll write the derivative in component form like that. Gets a little messy when you have the ij and k. And when our derivative is not the 0 vector, what it's going to do, if you apply it to the point at which you're taking the derivative, you get a vector that's tangent to the curve. So right away, you get a tangent vector. In Calc 1, Remember, you used to build the tangent line. You'd take the derivative, that was the slope of the tangent line. You'd get the point of tangency, and you'd build that line. Here, it all happens in one fell swoop. If we take the derivative, that gives us a derivative vector, plug in the t value, and boom, we've got a vector that's tangent to the curve at that point. And one of the nice things about this tangent vector is that it's going to point in the direction of increasing t. When we have our parametric curves, they will have, most of them will have an orientation to them. So there will be a direction that the points are plotted, which we call the orientation. And the orientation is the direction of increasing t. Direction of increasing t. And the not unit tangent, the tangent vector will point in the correct direction. It tells us which direction the curve is being plotted. Gives us the direction of increasing t. Now, we've talked a little bit about unit vectors, and here we're going to start talking about unit vectors again. It's going to be really important to be able to create a unit tangent vector. The reasons why are kind of complicated. We'll get to them later. But one of the things that's helpful if you have a unit tangent is to determine the curvature of the curve. So curvature is a measure of how quickly a curve is bending. And if you use the unit tangent vector, you can sort of use it like a gauge. If you have a unit tangent vector as opposed to tangent vectors that are of all different lengths, you can use that to define a measure of the turning, the curvature of the curve. And it will turn out, I'll say it right now, I'll repeat it, though you don't have to write this down. The curvature, let's think about a circle. Curvature of a circle is the reciprocal of its radius. So the bigger the circle, the less the curvature. Right? The bigger the circle, the slower the curve is turning. The smaller the circle, the quicker it's turning. So curvature will be the reciprocal of the radius. And so with a curve, you are familiar with finding tangent lines, which are considered the best linear approximation to a curve. And in Calc 2, you did something called the Taylor series. And that was giving you the best quadratic approximation, or best cubic approximation, or best quartic approximation, depending on how far you went out in the Taylor series. And with curvature, what we're going to do is talk about the best circular approximation. So the best circular approximation at a point, so maybe that's the best circular approximation at this point right here, and we'll have a method for finding this. This is called the circle, this is called the osculating circle. Not oscillating, but osculating, different from oscillation. Osculating, I think in Latin it means the kissing circle or something. So the osculating circle is very frisky. And its reciprocal, the reciprocal of the osculating circle, will give us the curvature. So the curvature, we're going to use a Greek letter kappa, will just be 1 over the radius, and we'll call that the curvature of the curve at that point. So we figure out the osculating circle, find the radius, take the reciprocal. That's going to be the curvature. At this point, just think generally in your head, the bigger the circle, the less the curvature. Because the curve is going to be bending less quickly the larger it gets. So it's going to have smaller curvature. Curvature is always a positive number. I should say a non-negative number. A line has no curvature. The curvature is 0. So curvature is a non-negative number. So at any rate, that's part of why this unit tangent vector is going to be important, because that's going to help us. It's going to act like a gauge that can help determine the quickness at which a curve is turning. So the unit tangent vector is found in a way that should be pretty obvious to us by now. If we take a vector and we divide it by its magnitude, we've seen that, yeah, that generates a vector that has 1 as its length. Take a vector, divide it by its length, you have a unit vector. So that's going to be our unit tangent vector. And we imagine unit tangent vectors on our curve. You know, depending on the orientation of the curve, if the orientation is to the right here, you know, we're just imagining these unit tangent vectors all along the curve. Whoops. Unit tangent vector. You know, so we imagine the unit tangent vector along the curve, and it's always going to be pointing in the direction of the orientation for the curve. All right, so Yes, there's a million rules. Do not write these down. They're the same old rules that you had in Calc 1. Derivative of a constant will be 0, but in this case it's the 0 vector. If you differentiate a constant vector, you get the 0 vector. The derivative of a sum is the sum of derivatives. The derivative of a product, where you have a function times a vector, you're going to use the product rule. So even though this is a function and that's a vector function, this is a real valued function and that's a vector valued function, product rule is still the same. Derivative of first times second plus first times derivative second. No big changes. Chain rule still works the same. Here we have a function inside of a vector function. Derivative of the outside evaluated at the inside multiplied by the derivative of the inside. So all those are the same. The one that is different is the one that's going to that we want to pay attention to, that's important, is this one. The dot product one, it doesn't matter which direction. It's sort of that product rule thing, f times g prime plus f prime times g. It doesn't really matter which way you do it as long as you take the derivative of one and match it with the other, and then the derivative of the other. It doesn't matter what order. This one, it matters because cross products are not commutative. So what is nice is if in Calc 1, your Calc 1 teacher just does the product rule this way all the time, derivative first times second plus first times derivative of the second. So derivative first times second. Did I say that right? Derivative of first times second plus first times derivative second. Because that's how it has to be here. You have to have it in this order. It has to go derivative first times second plus first derivative second. You know, so that you can't, if you switch any of these guys, you change the sign of your answer. Yeah.
Just making sure with the derivative of dot product and cross
Yeah,
product
sure.
rules, the dot and the cross product inside, are those dot or cross products, or is that just multiplication?
So that's a great question. So we always need to look at the context. This is a dot product.
Okay.
That is a dot product. But right here, that would be a scalar, regular scalar multiplication. That would be scalar multiplication. That would be scalar multiplication. So it kind of depends on the context. Whenever you have two vector functions next to each other, you assume it's a dot product.
Okay, cool.
If you have a scalar function and a vector function, it's a regular multiplication. And if it's a real function and a real function, it's regular multiplication. Yeah, so it's from the context. You've just got to kind of piece it together, which is which. Okay, so yeah, so these are all very easy to prove. If you let u equal u1, u2, u3, let v equal v1, v2, v3, you can just sort of go through the mechanical combining of all the components, and it will come out. Nothing complicated in terms of proving it. So we integrate vector value functions in the same way that we differentiate them, term by term. So we just jump in, integrate each component. And so the way that they've written this answer up here, they're writing this as a vector antiderivative plus a constant vector. So you can write it, you can think of it that way. In practice, we typically are going to have, typically we would combine these corresponding components and write our answer as a single vector, not with the constant separated. Usually we write that as a single vector.
Just plus C after every single one.
Plus C after every single one, or you could put a plus C with a vector symbol over it on the outside. So that would also work. That would also work. All right, so definite integral, same thing. Integrate term by term by term. Just evaluate each of them, plug in your upper limit and your lower limit for each of them, and you would get your values for each. So let's try it. So let's integrate here. So they say, find a tangent vector. I said let's integrate. It says let's differentiate first, then we'll integrate. So tangent, find a tangent vector at the given value for the parametrized curve. So derivative of r, not too complicated. We just go term by term. So we get e to the t, 3e to the 3t, and then 5e to the 5t. So that is the derivative vector. And we can think of the derivative vector as forming a tangent vector to the curve. Now they ask us to find the specific tangent vector when the t-value is 0. So t-value of 0, we plug in a 0 in here. We get that. So what you're visualizing, first off, is that you've got some curve in three-dimensional space. We know we're in three-dimensional space because we've got 3 components, and we know it's a curve because there's 1 parameter. So it's got some squiggly thing in three-dimensional space. If you take the derivative, you're going to get a vector. If you want to get a specific vector for a specific location on the curve, you would plug in a specific t-value. So this is the derivative vector when t is 0. An obvious question is, well, where on the curve do we imagine this little vector being applied to the curve? So what we would do is plug in t equals 0 into the original function to get our location. So this will give us our location. So 1, 1, 1. So we're imagining our curve in space. 1, 1, 1 is on the curve, and then we've got this vector 1, 3, 5 that's pointing off of the curve at that point, tangent to the curve. Question, Grant?
That t is supposed to be small, yeah, on in the 5.
That one right there?
Yeah.
Yeah, it's supposed to be small.
Okay.
Yes. Yeah, actually, I saw one of the homework questions. I don't know if it was just on the computer. I was looking on a laptop. And there was one question I was doing, I think it was in 11.5, where the exponent didn't really look like it was up in the exponent position. I don't know if anyone had that experience. Beware if you see one.
There was like.
There was one question.
There was one question where it was like hard to see.
And it was e to the 5, and the 5 looked smaller than the other numbers next to it, or something. And I was surprised because it didn't look like an exponent, but it was.
There's one that has a navigation error too.
Which one was that one?
I think it's like 11.4, like number 7 or something. If you get it right, it'll say try again. I mean, you can still go to the next one. You just have to click the arrow instead of continue.
Okay.
I think I had that too.
Okay, and the same type of navigation problem?
Yeah, I got some sort of error, and then I just kind of refreshed the page and it fixed itself.
Huh, okay, I'll look at that one. And so for you, you refreshed it, you clicked similar exercise and did it again, or?
Oh no, I just clicked the arrow at the top that moves you to the next problem. Usually you can click like the blue box at the bottom, but every time you tried that, it would like reset the question, give you a similar one.
Yep.
So. But you can just move on manually.
Okay, all right, I'll look at that one and see if I can recreate the error. Okay, so the idea here then is that this is a point on the curve, 1, 1, 1. This is a tangent vector at that point. So at that point on the curve, that vector is going to be nice and tangent to the curve. And if the question said find the unit tangent at 0, the unit tangent vector at 0, well, we would take our vector 1, 3, 5, we would find its length, and we would divide by its length. So that's 25 plus 10, so 35. So our unit tangent vector at this location would look like this. Our unit tangent vector. That would be the unit tangent. Mm-hmm.
So you said the r prime, that's tangent to?
Tangent to the curve.
That curve?
That curve.
Okay.
That thing up there, whatever it's doing in three-dimensional space, this will always be tangent to it at the point of application. So if we plug in t equals 0, we get a numerical vector. Mm-hmm. That's going to be tangent to the curve at the corresponding location. So we go up to the curve, plug in 0. So if we figured out the tangent vector when t was equal to 3, we get a numerical vector. Then we would plug 3 into the position function and figure out where that tangent vector lives. Okay, so let's do this one. All right, why don't you guys do this one? This one's not super complicated. So figure out the tangent vector at pi. tangent vector at pi. The only piece of this derivative that might hang you up a little bit, everyone clear on how you use the chain rule there? So we get 1/2 cosine of t over 2.
Oh my gosh, I did it right.
You did it right.
Wow.
Finally.
I remember something.
Yay! Did you plug in pi properly?
I think I did. I got negative 2, 0, 0.
Everyone agree with that? Yep, so that's our tangent vector at pi. And then if we wanted, then if we wanted the location, so the location we would plug pi into our position function if we want to know where we're applying this tangent vector. And so then we get sine of pi is 0, cosine of pi is negative 1, so that's negative 3. Plugging in pi there, sine of pi over 2 is 1.
Because you have t over 2 there, right?
So we're imagining that vector is being applied at that point on this curve in three-dimensional space. Make sense? Yeah, question?
Will you refresh me real quick on why it's 1/2 cosine t over 2?
So this right here?
Because it's like the derivative of sine of t.
Derivative of sine is cosine of the same angle, then multiply by the derivative of the angle.
So you take away the t.
Yeah.
So,
Question or? The 0, negative 3, 1. So that's going to be the point of application. And in three-dimensional space, we're not going to really do this. We'll talk about it in a conceptual way, but the idea is maybe that's the point, 3, negative 3, 1, and then the tangent vector will be applied right there. So this would be r prime of pi, and we're in three-dimensional space somehow. This vector right here would be r of pi. So r of pi connects you to the curve, and then you apply the tangent vector at that point. So.
Can I ask
Yeah.
if I'm getting it right?
Sure.
So it's to say at that time, at pi time, that this is where we would be at, but that's how it's behaving at that moment?
So if one way to think about it, if you took the magnitude of the derivative, that gives you speed. So if you're trying to think of an application like a projectile motion or something, the length of the tangent vector gives you the speed at t equals pi. What's that? So the r vector is giving you position. The derivative vector is giving you velocity. So if you take the derivative of r and get velocity, the magnitude of the velocity vector is the speed at that moment. So if this is the path that our projectile is taking, this is the location at t equals pi seconds, and then the length of that derivative vector will give you the speed at which that particle is moving at that moment. So you can, and it's also giving you the direction, the trajectory of it at that moment. So the derivative is giving you a couple of things. It's giving you the direction that it's moving, and it's giving you the speed if you take the length of it. Yep.
So I could be wrong about this, but this goes back to like visualizing the functions in 3 dimensions. So what you
Mhm.
said earlier is that this would be something elliptic in shape because it's got a parameterized t function. We have sine and cosine for the z. You're the parameterized, all of them parameterized. And in my mind, because trig functions oscillate,
Yep.
does that mean that the z function is going to oscillate and you get something that's multi-valued?
So no, it's not, it's still that's a great question. So like with those, this is a very funny thing because with parametric curves, these are all functions, right? When you plug in a t value, you only get one output, correct? I can't plug in a t value and get 2 different points at the same time. So definition of a function says if you plug in an input value, you get 1 output value. So it is a function, but like a helix, okay, it's a function of t, but if you did the z-line test, it wouldn't sort of pass that classic definition of a function because there's multiple points along the same vertical line. But so a parameterized curve can be a function that's not a Cartesian function. So like if you think about a unit circle, the parameterization for a unit circle, r of t, the standard one, is cosine comma sine. I should put a t instead of a theta. This right here, this is a parametric function. If I plug in a t value, I only get 1 output. But graphically, it's not going to be a Cartesian function.
Right.
So
the question is, if you were to try to determine whether that was an actual function, would it just be that all of its inputs are functions, or
each input gives you a single output.
Okay.
So when we look at that vertical line test type of thing, this is a Cartesian function because no matter what, if I plug in this x value here, I get 1 y value. This is not a Cartesian function because I plug in that x value, I get 2 y values. But it is a parametric function because the t value here is different than the t value there. So you get 1 point per t value. Even though those points can line up and have the same x value, it doesn't matter. It's a parametric function, but not a Cartesian function. So now your point here, these 2 components here, that gives us an ellipse in the xy plane. And as we're moving along that ellipse to calculate what our z value is, this is going to give us a z value that is depending on what the t interval is. And this looks like there's no restriction on the t interval. So we're going to have oscillation of the t value. So in my mind, I sort of think of this as an elliptic roller coaster. So we're going to have this elliptic shape if we look down at it. But as you're moving along it, this is going to be bouncing around between -1 and 1. So we've got this elliptic shape if you look down from above, but then the z values are oscillating between -1 and 1, so it's going to be going around like that. Does that make sense?
Yeah, it does.
Right, because the sine values, if we have no restriction on t, they have to bounce between -1 and 1. So the z values for each of the points on this ellipse right here will be, up or down. So we'll get some sort of elliptic roller coaster. The elliptic roller sounds awesome. Let's go to what's that place? I haven't been on that crazy roller coaster in so long.
Those make me
That
sick.
scary wind roller coaster down the street. What's that?
Lakeside.
Lakeside.
The Cyclone
Lakeside.
Lakeside.
Is that place still open?
Yeah.
It is still open.
Yeah. It's $10 instead of $80.
Yeah, exactly.
I don't have to refinance my mortgage to go there.
Yeah, exactly. Yeah, you can tell why when you're on the roller coaster. So find the unit tangent vector for the following parametrized curves. So go ahead and do that. So find the unit tangent vector.
So is that just what you did this time?
So you're going to find the derivative, divide by its length. So, but now notice one thing, they're not asking you to plug in a particular t. So they're asking you to come up with the unit tangent function.
So it's going to have not
It's going to have a
numbers
t,
on the
it's going to have
bottom?
t's in
Okay.
it. Yeah. It's not going to be all numbers in the bottom, right?
But it's gonna
So just like in Calc 1, the derivative, you can think of it as a function. It's a slope predictor. Same idea here. We have a tangent line or a tangent vector predictor.
Oh, yeah. Okay. Just ends up
Are you
turning
sure?
one
We have to take the
Okay.
back.
Got it.
Really remembered something.
Yeah. I remember the harder of the.
I assume it would be the
Or you can kind of
So you find the length of this. So you square, add, take the square. So you can have
it'll be like oversized.
yeah, you can have a variable. You can have a variable length.
You can have, okay.
Yep. Yep. So now in this case, well, you'll see in a second. Figure it out.
question. I'm thinking it's probably an integral.
One for the
From
Yeah, so exactly. So the magnitude is 1 there, so
and then it
the derivative
turn it into.
is already a unit tangent vector.
Yeah.
So what do you get when
Well,
you
that's the way
simplify
I
that?
think of to get
Oh,
an objective magnitude.
Yeah, so that denominator is turned into 1, so the original derivative is exactly.
That's pretty much what I found out. I kind of used pi Pythagorean theorem.
Yeah. So the magnitude of that is 1, so you're
That's not what it is. I don't. Cosine squared is sine squared is 1.
Oh, yeah.
wait a
See, I didn't
minute.
get
So
that.
now we're
I
gonna
didn't
find
take the
the
derivative
magnitude.
of this.
Wait, is this what it ends
Square
up
root sum of
being?
squares.
Isn't it just one?
Doesn't matter if there's a t in there. It doesn't matter.
I love
So,
my
I love math.
Take the variable.
So it's, then it's just,
Dependent
yeah,
on
then
t.
it's,
I
forget
love
that I wrote
math.
that, so it's just that.
That was so sweet.
Oh, how
Negative
sweet
sine
it
t,
is to be
cosine
doing
t is
the.
0. The magnitude is just 1, because this is just
How
sine squared.
sweet it
Cosine
is.
squared is 1. Square root of 1.
So any questions on derivative vector? Just take a derivative of each component. And now we're going to find the magnitude of this. And we'll have to have our Pythagorean identity remembering event. So sine squared plus cosine squared is 1. So it turns out that r prime in this case is the same thing as t. So you can think of t as a function. It's going to give you the unit tangent vector at different little t values. Plug in a particular parameter value and it gives you your derivative vector.
Yay.
Yay! All right, let's try this one. This one will be a little bit different. So r prime will be 2 times e to the 2t, comma 4 e to the 2t, comma negative 6 e to the 2 minus 3t. Get that? So I didn't put the of t. We get sloppy doing this. You can put it. You don't have to put it. It's one of those things. It's up to you if it helps you to think of it as a function by having the of t in there to remind you. Keep it in there. You don't have to put it in. So then we find the length of this derivative. That's the square root sum of squares. So this is the part that we didn't plug in a particular t value, but we can still find the length of this. We can still find the length of this as a vector. So we're going to square everything. So when we square this, we get 4e to the 4t plus 16e to the 4t plus 36e to the minus 6t. Not a lot we can do in here. Looks like we can combine the first 2 terms only. What's that, 20e to the 4t? Now, of course, you could take that negative 6t, you could put it down in the denominator, you could get a common denominator, and you could simplify it in some ways. I'm just going to leave it like that for the time being. So that is the length of the derivative vector. Any questions up to that point? Yeah?
Are we gonna get a way to find the unit vector without being all ugly?
No.
You think it's ugly?
Sometimes, not always.
Is
Is that one bothering you?
I know. I don't like where this is going with that. You're not there with that.
Wait till we take the derivative of t.
Oh.
Okay.
No, thank you.
Yeah. Yeah. So there is.
Like the derivative.
So t. So when you think about your curve in space, you can create a unit tangent vector, and then the next step is going to be to create something called the unit normal vector. And the unit normal vector will be perpendicular to the unit tangent vector, so the curve will be here, and the unit normal vector will always point to the concave side of the curve. And to get to that unit normal vector, you have to take the derivative of the derivative. So right now you should feel grateful.
Okay, I'm grateful. I'm grateful.
Hey, you're grateful right now that you don't have to take the derivative again. Okay, so now to get our unit tangent vector, we're going to divide magnitude r prime into r prime. So we're just going to do term by term. And there's a couple of different ways you could write this. Some people would just leave this under the whole vector or write it as a coefficient. It doesn't really matter which way you do it. It's going to be ugly no matter what. So this will be our derivative, our unit tangent vector at t. Unit tangent vector at t.
Do you prefer it like that on exams?
It does. I don't really care. If you wanted to just write it underneath the whole thing, it's totally fine. Okay. Totally fine. A lot of books will always force you to keep it separated like this.
And then type it all into MATLAb.
Yeah.
Oh, do you have to type all that
I like
in
typing
MATLAB?
it into MATLAB.
No.
There's this great function called
Copy and paste.
Yeah.
Also, \SQRT puts in the square root without having to move your hands off the keyboard.
Off the keyboard. Yeah. There's a few of them. There's a few
Yeah, there
keyboard
are.
commands, right? Because you can do Control Caret to get the exponent, right?
Yeah, I'm pretty good at those over time.
Yeah.
Yeah, you get your fingers just like
Is there a
automatically move after doing it. Yeah.
It's taking me 2 weeks.
Oh, Control Dash.
Yeah.
You got the whole list.
Once you have to write it, it's like,
no.
All right, so that's the derivative divided by its length, so that gives us a unit tangent vector. If we wanted to find the unit tangent vector at a particular value of time, we would just plug it in and simplify it. Just. Okay.
Why does mine look so much different?
This is prime.
I don't know. All right, we ready for a chain rule?
No.
Product rule?
That vector is a violation of
So we want to find the derivative of this. Okay, so first off, let's write out the formula we're going to use. So U cross V. So we just have to be consistent. And you can be, there are two ways you could write it. The most important thing is that U comes first in both of these. So I'm just going to write this down first. So U is going to come first in both of them. So you can do first derivative second plus derivative first second. That totally works. First derivative second plus derivative first second. Or the way they wrote it in that chart, which is why I got tangled up saying it, if they wrote it this way, which actually is not the way that I normally think of it.
But as long as it's UV plus.
Yeah, as long as U is first in both of them, it works fine. The piece that you can't flip-flop is this. Like a lot of times in calculus 1, they'll say first derivative second plus second derivative first. That's the piece you can't do. First derivative second plus second derivative first. The order has to be the same. You have to have FG, FG. So
That's how you do it.
yeah. Yeah, first derivative second plus derivative first
you can
second.
have derivatives.
You can have
wherever
those.
you want.
Yeah, you can have those wherever you want, as long you can either have the derivative coming first or it's coming second
Right.
of the
And then
U.
just the
As
opposite
long as
on
it's
the
U
piece.
and V, yeah.
Okay.
As long as you don't switch and have V times U. Okay, so this will be u. Let's see, I don't want to write that yet. Let's come up here and write the derivatives just below these. That might be a pretty efficient way to do it. So u prime will be 2e to the t, comma 2t, and v prime will be negative 1 minus e to the minus t, comma 1. All right, so you got
I
those.
just rewrote it.
Questions?
Okay.
It's just different than the notes.
It's, yeah, it's like weird.
I just think it's a
Which
different,
part's weird?
like completely different problem.
I think it's just a different.
Oh, that's funny.
Yeah.
Oh.
It was just like, wait, where?
Yeah, where did that come from? Huh, I don't know. That's funny.
I just crossed out the other one.
Yeah, we'll do this one.
Oh.
I don't know how that got changed.
Wait, we're not doing the one in our notes, or we're doing that one?
You're doing the one in your notes when you leave. Right now, we're doing that one.
Okay.
Is
well,
that one
that's the
anyway?
one.
I don't know how that got switched. I'll go figure that out. Figure it out for next semester. Okay, so u times v prime. So we have to do u times v prime. So we have to do those two. So it might be easy. I don't know. The more you do these, the more you get used to just sort of seeing which ones get multiplied together and which ones don't. It's technically easiest if you stack them really nicely. Then you have less chance of making a mistake. Yeah.
So you just said times in that right equation. Does that mean that u cross? That's not u cross v prime. It's u times.
It's u cross. It's times means either dot or cross depending on the context. So times in this case we mean cross.
Okay, just wanted to make sure.
Yeah,
that
yeah.
wasn't-
Yeah, I should say cross. Yeah. Yeah, so u times v prime. Okay, so let's try to do this now. Here we go. So these two being multiplied together, we're going to cross out the first column, and then it's going to be e to the t minus what happens when we multiply, oh gosh.
Yeah, this is ugly.
That is ugly. This times this, right?
Ew.
Ugh, that-
Wait.
That's a good one.
Right?
Crossing out the first column?
Crossing out the first column, and then it's going to be that times that minus this times that.
Oh, because you have to use all of it. Oh my
Yes.
gosh.
All right, I think I can do it. So plus t squared e to the minus t minus e to the minus t.
That's almost the truth.
Yeah.
I think that's right. All right, next one. That's only the first component of this first multiplication.
Wow. Gotta love it.
All right, let's see
Please
if we
tell
can.
me we don't have to take the derivative of this one day.
We don't have to take the derivative of this one. It makes us feel better. Okay, so now we're going to cross out the second column. So crossing out the second column, let me move these guys out of the way. So second column is gone, and we're going to end up with 2t. That's the main. Oh, and then we have to switch signs. We'll keep that on the burner. So the middles are crossed out. We're going to get 2t minus a plus 1. Oh, plus the t squared. Oh, dang it.
T squared minus 1.
Yeah, t squared minus 1. Does everybody see that? So we're going to get 2t, and then minus, but this is going to turn into a plus t squared minus 1. So plus t squared minus 1, but then we have to switch the signs. So minus, minus, and plus. Woo. Probably going to be easier to write them down stacked.
Yeah.
And then we cross out the third ones, and we're going to get 2t e to the minus t. 2t e to the minus t. So that's that times that. Oops, that times
No,
that.
that should be a negative 2.
Oh, negative. Should be negative. Yeah, negative 2t e to the minus t. Minus a minus, so plus e to the t. So there's that one.
Hey, so for the second term, we got negative 2t plus t squared. What's a little...
That's a minus t squared, yes. Yeah. That's the changing of the signs.
Where did you get the last one?
So the last one comes from crossing out, we're crossing out those guys, right? So it's going to be 2t times this, so minus 2t e to the minus t, minus
minus a minus.
minus gives us plus
Okay.
e to the t.
It's much easier to see it when you stack.
Yeah, if you
for
stack,
sure.
yeah, if you
Then
stack
you
them,
can
it's
like
gonna
cross it out. And you
yeah,
don't have
then
to
you
do
can cross
crossing
it out.
out
It's
on
gonna be
both
a lot
sides.
easier.
I think it implies
Holy
that
moly, okay.
we pram under the U vector is way easier to see.
Much easier to visualize. I totally agree. That's definitely how I would do it. And then the last one, we have to do u prime, so this one times v. So we're going to cross out the first columns. Yeah, let's do that actually. let's make it easier on ourselves. So u prime is 2 e to the t, 2t, and v is minus t, e to the minus t. Yeah, do it in a way that makes it visually pleasing. So here we're going to get t e to the t. So t to t minus 2t e to the minus t. And then our
just sound like a made up language.
it does. I feel like we're speaking some Klingon. So then cross out the middle, and we're going to get minus 2t squared minus 2t.
Minus 2t squared minus 2t.
Minus 2t squared
I know.
minus 2t. And then the last one is going to be 2e to the minus t
Oh, I'm
Plus
seeing it
TT.
now.
plus te to the t.
You can do that one.
All right. Whew.
Just that one last one.
And now we have to combine our corresponding components, which will be left for you to combine the corresponding components.
Looks like some of them cancel out.
Some of them hopefully cancel out. I would not give you one this
Intense.
Ugly.
head-aching, this mind-bending on a test. Exactly. So add the corresponding terms. It would be a lot easier if they said figure this out at t equals 0. Then we could plug in 0 and that would be easier.
Yeah, it would be
You
like
do that if you do something like this?
Yes. I gotta make that's just that's just busy work.
Oh yeah, you're in there.
There's no value in a whole bunch of visual. All right, what day is today? Wednesday? All right, see you guys on Wednesday of next week. On Wednesday. On Wednesday of next week. Have a great weekend.